So I'll talk about the research paper here today. So let me see if I can share the screen. So can you see this?
Yeah.
So I'll talk about this research paper, which is titled as what makes data suitable for a locally connected neural network, a necessary and sufficient condition based on quantum entanglement. So the topic of the paper is that there are certain kind of data sets which are optimal for deep learning models, which means that this kind of models, so when certain kind of data sets are used to train a deep learning model, it produces good predictions. But on the other hand, there are other kinds of data sets which does not produce good predictions. So what kind of properties must exist in a data set? The data sets exist what kind of properties that produces good predictions. So that's the thing that they're trying to determine.
Okay.
So the structure of the paper is that first of all I'll just give the brief I'll show all the structures of the paper, all the sections of the paper. Then I'll go step by step and I try to explain all these sections as much as I can. So the first section is introduction. Then there is the related work where they talk about some previous works. Then the third one is the preliminaries, where they define some technical definitions that they use later on to explain their things. And then we have section 4, which is titled as this, and then we have section 5. Okay. Then there are other sections as well, section 6 and 7, which I'm not going to too much because I haven't covered it, studied that part. So this is it. So I'll start with the introduction. So if I change the tabs, can you see them?
Yeah, I can.
Okay. These are the data. So there are some data distributions that work well with deep learning models, while others fail. So yes, again, so some deep learning models that achieves outstanding performance on certain kind of data distributions, while some distributions, while training on data sets with other kind of data distributions, it performs poorly.
So like, what do you mean by data distributions?
Yes, that's why I have highlighted it in red. And another thing I'm going to highlight is this thing. I'll talk about it too. So this question means this question came to me as well. So I tried to look up to some definitions. So this is what I got. The data distribution means it refers to the statistical characteristics of the data set. So I think it means that the mean, median, mode, but that's not the only thing. I've tried to inquire more about it, and it's not just the mean, median, mode. It's also about the distribution. Things like normal distribution, whether data set is normal distributed or binomially distributed. Have you heard of such things? Normal distribution.
Yeah, I remember slightly about them. Yes.
Okay, so there are data sets. So data can be distributed in different kind of shapes. So let me see if I can. These are examples of certain distributions. Can you see the shape?
Yeah, and this is called like bell curve or something, right? Bell
Yes,
curve distribution.
bell curve. Yes, bell curve. This is a bell curve distribution is another name for normal distribution. So this is one it is. Then we have some other kind of distributions such as binomial distribution. The shape is similar, but the properties are different. That's the thing is. We have geometric distribution. I think so. Yeah. It's shaped a bit different. So the point is that the data sets can have different kind of distributions and different properties. In here the data means that each feature column. So you might know about the different columns that exist in a tabular data. So each column is a feature for a in the context of machine learning. So different features, each of them might have a different kind of distributions and different properties. So in this context, that is what they are trying to define. Data distributions means the properties, the distributions, the statistical characteristics of each and every feature column in the data set. That is what they mean by data distributions. Okay, that's one definition. Now I'll talk about LCNNs. The next thing, what they say is that the author of this paper primarily focuses on what kind of data distributions are suitable for accurate predictions for a particular family of neural networks called locally connected neural networks. So in this paper, they have studied about what kind of data distributions are suitable for one particular set of neural networks, not for all neural networks in general. Only this family of neural networks, which are known as LCNNs. So as per the research paper, these are the kind of neural networks which they call to be neural LCNNs. So by that, what I understood is that the connections between the different nodes, not all nodes are connected to each other. I think that's what I mean. That's what they mean by LCNNs. For example, if you look at, I don't know much about convolutional neural networks, but I have studied RNNs. So in an RNN, okay, we have the layer that comes before it is, suppose there is a layer n. It is only connected to layer n minus 1 and n plus 1. The one that's just above the before it and the one that comes after it, as well as it's connected to all the other nodes within its own layer for a recurrent neural networks. But it is not connected to some other layer that is beyond its immediate neighborhood. Did you understand this part?
Yeah, somewhat I understood.
Okay. So this is unlike, so what I assume, the opposite of LCNNs would be certain neural networks where they are connected to all the other nodes within the neural networks. For example, I think so graph neural network is one example. It could be.
Are
It means
those called fully connected neural networks or something? Because I think
maybe,
I remember hearing that term
maybe
somewhere.
I'm not sure, but it could be, because again I don't have any paper, but that's what it is. Suppose, let me simple I want a simple neural network. So here you can see, suppose there are 4 layers. So suppose this layer is connected to the layer which comes before it, and the one which goes after it. This layer, the third layer, let's assume this to be the third layer, it is not directly connected to the first layer. It is indirectly connected, but it is not directly connected. So I think so this kind of neural networks are called locally connected. That means the one that are in its neighborhood, only to those kind of nodes that they are directly connected. But I think so what you have said, a fully connected neural network, it might be that it is this one's directly connected to this layer as well. So it could be like that, I think so. So I have never seen that. Let me see what's the
So
diagram
then
of it.
the mostly used neural networks are LCNNs then, because that is what we hear, right?
Yes,
CNNs, RNNs are the ones we study, or that is what is taught. So mostly we are taught LCNNs.
Yes, yes. So I think so, yes, means as of now, mostly I think so LCNs are primarily used. As fully connected or things, yes, the non LCNs are I think so much more newer in, it's a newer invention. It looks like that. So yes, so far that's what they're going to do. So they are trying to, so in this paper, what they're trying to do is trying to find out what kind of data distributions are suitable for accurate predictions for LCNs. Okay. Now, how do they do this? But before that, there is one thing that there is an intuitive idea about it, about what kind of data is suitable. So here they mentioned that data which exhibit a local nature. By local nature, they means that features or patterns that are spatially or temporally localized. So what does that mean? I think I haven't gone through in depth about this definition about what local nature technically means, but it seems like they are not connected, means they are independent of, means a certain feature is independent of some other feature. I think so. It's
That is what is used for PCA or something,
yes,
right?
yes, exactly, PCA. Yes, I think so. Yes, while normal pre-processing, it means people are regularly use PCAs, and there's another term called cosine similarities and all of those things. Means they try to determine whether they are correlated or not, and if they're correlated, it's used for dimension reduction, is to get rid of features that are similar in nature. So I think yes, I think the concept of local nature seems to be that if there are features, if all the features are unrelated to each other, that means it's a good data set. So intuitively, I think so. That's the broader idea about what they're trying to say. But that's the intuitive idea. But there is no quantitative or mathematical definition about that. Okay, if we find a data set, if we do some mathematical studies, then or if it satisfies this kind of conditions, then it for sure will give a good prediction. We can't say that as of now. It's just an idea that okay, if there is less correlation between the data sets, that means yes. If there's less correlation between the different features of the data set, that means it's a good data set. But that's not the mathematical way of going about it. It's just a very intuitive way. So in this paper, they're trying to come up with a mathematical framework. By using this framework, anyone can, if anyone can, what they can do is that they can go take their data and go through these steps. And if the data set satisfies these properties, then they can be mathematically sure that the data set will give a good prediction. So that's their goal. And so, how are they going to do this? Next, that's what they're trying to. The next thing is that's what they're trying to explain here. So what they have said is that in machine learning so far, there isn't such kind of mathematical tools available to determine the goodness of a data set. So there is another scientific discipline as per the paper. What they say is that there is a distinct scientific discipline that studies a similar problem of tying distributions and computational models. Okay. And this discipline is quantum physics. Here, distributions of interest, that means data distributions, are described by tensors, and associated computational models are tensor networks. I'll describe everything in details. I'll just first read through this. And unlike in machine learning, where there are no accepted mathematical models, in quantum physics there exists a widely accepted theory that allows for assessing the suitability of data distributions to computational models. And this this theory is based on the notion of quantum entanglement. So what have they done here? They have drawn an analogy between machine learning and quantum physics. And they're trying to show that if they can show that a machine learning model is mathematically similar to a system that they're studying in quantum physics, then the tools that are available in quantum physics can also be used in machine learning as well. That's what they're trying to do.
I'm not sure if I get this point. Can you explain again?
Okay, it's like, for example, you're trying to map a problem to an existing tool that is available. For example, think of a data structure like queue. It's an abstract data structure that something comes in from the back and goes out from the front, or anyway, front or back, whatever, and goes out from one side and goes out from other side. Now, if you take a real life scenario, suppose you are in a some kind of polling. Suppose you're designing a computer program where you have to, maybe you're in a voting station where people can come in from one side and go out from another side. You can then it comes to your mind, okay, this is a real life scenario, but I can model this thing. There is a computational tool. There is an abstract computational tool, but I can model this thing based on this model this real life thing based on this abstract computational tool. Or maybe another example would be, think of that tree data structure. And you might think, okay, and a real life scenario would be a family. There is a father, there is a mother, maybe there's a grandfather and the grandparents and the children. And you can see, okay, this is a real life scenario. If I have to visually show it, I can use a tree data structure. That's an abstract thing. I can use an abstract thing into a real life phenomenon to model a real life phenomenon. So they are trying to do a similar thing here. And I'll try to go into more details about how they try to achieve it. So how are they drawing the parallels here? Okay, this is the section 3. I'll go to section 3 now. So section 2 is related what means where they mention about the research attempts made by other researchers trying to do the similar things. And they have mentioned that, okay, there are other researchers who have tried to come up with a mathematical framework for defining what they're trying to do, but they haven't been as successful. And so they are trying to do this thing in their own paper. Okay. So okay, they mainly talk about two mathematical tools and this property here. Quantum entanglement is not a mathematical tool, but I'll talk about this later. So the two tools that they talk about are tensors and tensor networks. Yeah. So if you can see this column, there are three columns in this table. The first one describes the mathematical tool. The second column describes how this mathematical tool is used in quantum physics. And the third column describes how these researchers have used this mathematical tool in the context of deep learning and machine learning. Okay. So a tensor is, if you might know that a tensor is just a matrix, a multi-dimensional matrix. It's just a matrix, more than one matrix stacked on top of each other. It's just simple as that. So for a deep learning model, in terms of quantum physics, what are they trying to model? So this whole thing in quantum physics, they're trying to model a quantum system. Now, what this quantum system is, that is beyond the scope of this research paper, and they haven't defined it in details in their own paper. But what they have described abstractly is that it's a quantum state, and within this quantum state, there are different quantities, you can say, components of this quantum state. Think of it as particles, okay? Think of it as a box. Think of it as a box, and this box contains different particles. For easier understanding, a box containing different particles. The whole box is a system, and each and every particle is a component of the system. In the same way, in deep learning, the box can be thought of as the table, and each and every column is one particle in that table, in that box. Can you make the connection?
No, can you explain again?
Okay. Okay. Here's the scenario. In quantum physics, here's the scenario. Think of it. Think of a closed system. A closed system means, suppose it's a box. Okay, it's a box, a rectangular box, which contains particles. Suppose a box contains air molecules, and each air molecule within the box is a component of the system. The whole box in total is a system, and within the system, each and every component, each and every molecule is a component of the system. So far,
Component of the box, which is the system.
yes, the box is the collection of all the components in, and in total it is called the system. And each and every component, each and every molecule is a component of the system. And the properties of each component is stored in an suppose, okay, yes, the properties of each and every component. Suppose a molecule has weight, some other things like whatever it can be. So there are different properties of a molecule. The weight, the color. Actually, I'm giving an example of a molecule, but actually it's the in quantum system, the thing that it describes are quantum particles, which have this up down spins, and then there's flavors and all kind of things. So the tensor stores all the properties of these states of this system.
Mm-hmm.
If I can draw a diagram to be a little bit better, but okay. But the tensor part would be easy to understand in case of deep learning. So I think so you can make the reverse connection. If I can explain you what it means in deep learning, you'll be able to understand what it means in quantum mechanics. Okay, so in deep learning, for a tabular data set, it's a matrix. So that's easier to understand. That each and every column is a unique property, and each and every row is one example of that property.
Mm-hmm.
For example, take the suppose each and every, suppose you have a data set about the properties of a human. Okay, the height, weight, age, everything. So each and every column will contain, suppose first column is about height, second column is about weight, third column is about age, fourth column is about something else, or another property of a data set of the human. And every row is one entry about each one particular human. Can you understand this part?
Mm-hmm.
So in the same way, think about in quantum in that system. Each and every column contains one property of a molecule, and each row contains the value of one specific molecule within the system. Now, is it making sense?
Yeah, okay.
Let me wait a minute. There's no. Wait a minute, I'm trying to put up a whiteboard or some kind of writing instrument here. Okay, there are no, it's not available, but I'll try to draw a table here, which might be able to explain. Okay, are you able to see this part? For suppose in context of a deep learning model. So suppose this is a matrix. So suppose for person one, suppose whatever some values are there, and for person two some other values are there for height and age. So this thing you understand, but now yes, this is easy to understand. But now consider in case of quantum system, for each and so on. So this is the equivalent of that. Do you understand now? Something. I'm getting some idea about what I'm trying to say here.
So this is a tensor. You're saying this is a tensor.
This is a matrix as of now, but if I put multiple matrix on top of each other, that becomes a tensor. But
yeah, okay, I understand. Yeah.
let's assume that we are talking about a one-dimensional tensor, which is only a one-dimensional tensor is just it's nothing but a matrix. Okay. So what I'm trying to tell here is, what does a matrix represent in the context of deep learning versus what does a matrix represent in the context of quantum physics? It's a mathematical tool, but the data being used in the context of deep learning and in quantum mechanics for certain purposes. What are they used for? That's what I'm trying to say here. Okay, so here in case of deep learning, this they use a matrix to represent data, to represent tabular data. And in case of what can I say? In case of quantum mechanics, that they are using this table to represent a system. They represent the states of all the particles in a system.
Okay, understood.
That's okay. That's what this tensor is so far. Okay. Represents data, features, and all of those things in deep learning, and represents quantum states and their amplitudes. Okay, so that's the different properties of them. So what's a tensor network here? Okay, first I'll tell you what's the tensor network. This is a mathematical model, and how this mathematical model is used in deep learning. I'll tell you first that a tensor network for deep learning is nothing but it's the neural network. Okay, that's the neural network is nothing but the tensor network. And in case of quantum physics, there is no specific name called neural network. They simply call it tensor network itself, but it's the same thing. So I'll tell you what does that mean here? So in case of quantum physics, what they're trying to do is, at every time, suppose this table. This table describes the states of all the particles in that system at suppose time t equal to 1. And then in time t equal to, there will be some other table that will describe that the properties might change. So for each time span, there will be different table for that. Are you getting any idea about this?
Okay.
Okay. So there will be multiple tables. Okay. And just like think of a neural network. Suppose take any neural network. Okay. Suppose at t equal to 1, this is the state of the tensor at time t equal to 1. with all its properties. And at time t equal to 2, all the values of all the columns or the rows will change depending on the whatever change happens. And let this be the property, let this be the state of the matrix at time t equal to 2. Okay. And so what does, so each and every node, is it called node or edge? This is the node.
Yeah, it's the node.
Yeah, this is the node. So each and every node is the state of that matrix at each and every timestamp. And the edges here will most probably describe the probability of the transition between this state to this state, or maybe the connectivity between this state to this state.
Mm-hmm.
That's what it means in the context of quantum mechanics. And in neural networks, you already know what it means. There's nothing much to explain here. It's just the transfer of yes. So that was what then that's what tensor networks mean. Now the thing is whether, so now as I've said, they're going to use this mathematical tool in the context of deep learning. So that what tool do they use in the context of quantum mechanics? They see if this tensor can fit in this tensor network or not in case of quantum physics. And they use the following things. I think you mentioned this singular value decomposition. What did you mention? Was it
PCA?
PCA, yes. That is done using singular value decomposition, isn't it?
I think these are two different methods, but they are both used for dimensional reduction only.
Yes. Okay. So they are different. So these are the mathematical rules like canonical partitions, SVDs, and entanglement entropy. So these are the tools that they use to see if this tensor network fits this tensor, if this tensor fits this tensor network or not in case of quantum physics. So if they can somehow show that this thing here is equivalent to this thing in quantum mechanics, and a neural network in in deep learning is equivalent to a tensor network in quantum mechanics, then they can use this other, I think so we already know that SVD is used, but they can also use the other tools like entanglement entropy and other the canonical partitions and such other tools as well, to see if this data sets, that this data distribution can fit well in this LCNN or not. That's the idea behind their paper. I think they.
So when did this paper come out? It's 21 Jan 2024.
Yes, this year itself. I think they mentioned it somewhere. Okay, I'll say. Okay. Close to up. Okay, conclusion. Okay. So, just continue in the sequential manner, then it will make sense. Okay, so section 3 is then where they have defined what a tensor and tensor networks are. So in section 4, so far they have mentioned that a tensor, they can only do this thing by taking the tools of from quantum mechanics. But so far they haven't shown that is it actually possible or is it actually true. They've only mentioned that okay, we can take the data distribution, we can assume that the data distribution in deep learning is equal to a tensor in quantum physics, and a tensor network in quantum physics is equivalent to a neural network in deep learning model. But is it actually true, or they are just assuming it? But because since it is a scientific paper, you can't just assume the things. You have to actually prove it, that you have to actually defend your statement. by giving proper definitions and explanations behind it. So section 4 goes into those explanations, but it's too mathematical in nature, and I don't understand the full derivations. But I still got the main idea behind it. Okay, so if you look at the section 4, there are a lot of, yes, this is the section 4 here. There are a lot of mathematical definitions here, where but the main essence behind all these derivations is that they have proved that a tensor in a quantum mechanics that is used in quantum mechanics is equivalent to the data distributions of the data sets that are used in training deep learning models. And
Okay, wait. Can you come again? What did you say?
that the tensors that are used to store the states of the components of a system in quantum mechanics. A tensor in the context of, I had mentioned earlier that a tensor in the context of quantum mechanics is used to store the states of the components of the system, of this quantum system.
Yeah.
Okay. As I said, quantum system has many components, and each component will have some properties. And to store the states of those properties, a tensor is used. And they have, first of all, they have said that, okay, it's nothing but in the same way we store the features of a data set in a column and row in a tabular way. And so the tensor is the same thing. And in this section, they mathematically show the equivalence. So I don't understand the exact technical definitions behind it, but that's the idea behind it, that they have shown the equivalence here, that they are mathematically the same thing. That's the first thing. And the second thing is that, again, they have shown that the neural network is mathematically equivalent to a tensor network. They have not just initially they have just mentioned it, but in this section they have mathematically shown the equivalence, that okay, these are the same thing. That's the idea behind it. So in section 4 they have mathematically determined the equivalence. Okay, it's no longer just an assumption, or it's no longer something that should be taken at face value. They've mathematically shown the equivalence. So now that they have shown the equivalence, that they're the same thing, in section 5 they are going to use the tools that are used in quantum mechanics to show if a tensor, that I have mentioned previously, that in quantum mechanics what they do is they use the following mathematical tools to show to verify, to check that whether this tensor fits this tensor network or not. Okay, so okay, what did I do? So in the same way, they are trying to use the same tools to now see whether the data distributions here in deep learning can fit this neural network or not. In section 5, they are trying to do that.
And this is done mathematically via calculation.
Yes, they have done it here using through mathematically. I mean, they have what they have done is that they have shown here, they have shown that if the data distribution has certain properties. But wait a minute. Okay, if a data distribution if the data distribution satisfies certain properties, those data distributions will give good predictions when they are used to train a neural network model. And when I'm talking about certain properties, what properties are there? It's I think so. They have mentioned it. I mentioned it here. This is the part. Data that exhibit a local nature. Those data are good for good predictions. So again, local nature means they are I think so they are less correlated with other columns. Every feature column is as it's uncorrelated with the other columns in the whole data set. That's what a local nature means in the context of neural networks. So this local nature in context of quantum mechanics, what does that mean? It means quantum entanglement. So in quantum mechanics, quantum entanglement refers to the idea that two particles can be closely connected to each other, so much that if something changes in one particle, it automatically the same change is reflected in the other particle, to which it is entangled. So in tensor, in quantum mechanics, this thing is used to check for whether the systems or the components in this quantum system are they entangled to each other or not. So if something changes in one component of the system, is the change reflected in other components of the system or not? If they are reflected, that means they are highly entangled. If they're not reflected, it's not highly entangled. So that's how these tools are used in the context of quantum physics. But here, in deep learning, what they're trying to show is that quantum entanglement or the lack of entanglement means it's more local in nature. It's not one column is not connected to the other column, since they are not correlated. So so the idea behind this is checking for correlation. So in simple words, that's what it is. But here, what they have done is they have mathematically proven that if suppose now they have come up with some mathematical framework, and now what people can do is that if they take the data set and run through this framework, and they can see, and if it comes out that there's low entanglement between the data sets, that means it is mathematically verifiable that that data set is good enough. The data set will give good predictions if it is used for training LCNNs. That's the idea behind this mathematical framework that they have come up with. So as you can see in the conclusion that they have shown it. That's what they have mentioned here. Yeah. Our main theoretical result states that a certain LCNN is capable of accurate prediction over data distribution if and only if the data distribution admits low quantum entanglement under certain canonical you can ignore this part. It's just a mathematical way of saying things, but the idea is that thing. If the data distribution admits low quantum entanglement, what they're trying to say is that there's less correlation between the features of the data sets.
So ultimately their conclusion is the data, if there is low correlation between the features, then it is a good data set to train the neural network.
Yes.
But this conclusion was known from, I think, quite a while ago. So why did they have to compare it with quantum theory and its tools?
The thing is that they have come up with a mathematical certainty. See, there are certain things. Suppose, for example, you can see that what do we say? For example, there's some truth. Suppose every even number is divisible by 2. We say that. We intuitively know that every even number is divisible by 2. But can you mathematically prove that there exists no even number that cannot be that since there are no even numbers that cannot be divisible by 2? Does such a number exist? It's an even number but cannot be divisible by 2. It doesn't exist. You know intuitively. But can you prove it for all numbers? What if there exists a number? But if I bring it to you, can you for sure give me? The thing is that actually there are proofs. It's a very simple one. There exist proofs. But also at the same time, there are certain mathematical concepts which seems very simple, which seems very intuitive, and which is true for most cases. but every now and then you'll find some cases that it cannot be, that doesn't hold true. I think I saw a video a while ago. Maybe I'll show it to you later on. I'll discuss later on about such kind of things. That some things intuitively seems okay. It's definitely it's true, but actually it's not. In some cases, that statement breaks down. For example, sun rises in the east. It's intuitive. It's intuitive. Every day sun rises in the east. But can I mathematically prove that one day it will not rise in the east? We can't. It's the same idea behind this. That I know that in general, if there is less correlation, then that's a good data set. Intuitively we know. But can we mathematically show that this statement, if and only if, this means that now it's mathematically certain that if a data set is has correlation has columns with less correlations, then for sure that's a good data set. There's no doubt about it. That's the thing that they're trying to show here. That means that's the whole concept of a mathematical proof in general. One is intuitive understanding. The other is mathematically solidifying that principle.
So like, is this the first time this principle is being like mathematically written down?
Yes, I think they have said that there are two things: sufficient and necessary. In section 2, they have said. Okay, they have said again.
Because in PCA, that is the whole point of doing PCA, right? To decrease the correlation between features.
Yes, yes.
So but, the PCA is not based on actually any mathematical theory.
Yes. Okay, yeah, that's the thing. Means that's the thing behind engineering. The concept, the idea behind engineers is that okay, if they find that something works, it's okay, man. If it works, let's go with it. Their engineers won't wait for a mathematical truth to be verified before they proceed with their work. If some for practical cases it works, then it works. Let's go with it. If it's good enough, then let's go with it.
But so then, what is the history of PCA? How did we come across this concept of PCA? Because ultimately in PCA we are doing exactly this, right? We are decreasing the correlation.
See, I think so. See, this is my perspective. Is that if someone comes up with the idea and it works, then let's go through. Let's go with it. That's the attitude of an engineer or someone who's applying things.
Yeah, and that is what I'm asking. You're saying someone came up with the idea, but how did he come up with this idea? What is the history? Do we know that?
I don't know if I don't know the history, but I think so. Maybe there are some people who might know that history. That how did people come with that? But my hypothesis is that someone was probably trying to find out what kind of how can you pre-process the data set so that it gives good prediction. And suppose one person found out that if you reduce the correlation, I think so. It's a very intuitive thing. Suppose, okay, for example, there are two properties that could be very similar in nature. For example, I'm trying to come up with an example. Suppose suppose how good a laptop works, and two properties are maybe the what can I say? The RAM. That is not a good example, I think so. Think of something else. Oh, I can't come up with an example at the moment. Okay.
Anyway, it's fine. You can move on.
Okay, now let me spend some time because I have some partial examples. Okay, think of how much a machine learning model where we're trying to predict how well a student will score, how well a student will perform in an exam based on the number of hours that they have studied, and the number of pages that they have used to practice. Okay, suppose it's a maths exam and they are studying for a maths exam, so it's very important to practice a lot to perform well in a maths exam. For other theory exams, you can read without much practice also you can do quite well. So these are two things that are very much correlated. Suppose how many hours you have studied and how many pages you have used to practice. Okay, so if you have studied for a long hour, so intuitively you'll use more paper to practice. You'll spend time on practicing more questions, so and more paper will be used. So instead of using two different features, that number of paper used or the number of hours studied, those two will be more highly correlated. So you can use only any one feature will be enough for prediction. Are you getting this idea?
Yeah.
Okay, so I think so that's the idea behind. So you can come up with it intuitively that okay, what's the point of using two different features? It's almost the same thing. So okay, there might be some exceptions that okay, someone who is very into someone can do mathematics in their own head. So they will study a lot of hours, but they won't use much paper. So those are exceptions. But in general, most people, when they study for maths exam, they will practice a lot. And if they study for 5 hours, they may use 10 pages. And if they study for only 1 hour, they'll only use one page to practice paper. So it's very intuitive that there is a high correlation between it. So excluding those exceptions who are very talented. So in paper, so what they can do is they can study for 5 hours, they only look at the pages. And all their calculations make sense to them in their head itself. They won't have to use papers. So those are exceptions. But in general, the number of pages used to practice and the number of hours are highly correlated. So it's intuitively that okay, let me just use one features instead of using two. So you don't have to go through all those quantum physics and anything to come up with this intuitive idea. But that's just an intuitive idea. Now, can we say for sure that for every machine learning problem, if there are two features that are highly correlated, is it so? Suppose is it okay to get rid of one feature? Is it for every kind of problem? Is it okay? That's the thing. That's the thing. Okay, for some cases like predicting the performance of an FS student, it makes intuitive sense. But does it make sense for every scenario or not? So now someone might think that okay, it made sense for predicting this student performance. Now I'm using this machine learning model in some other context, maybe some from biotechnology. I'm using data sets from biological phenomena and trying to predict something else. Now, if two features here are also correlated, should I remove one thing? Okay, maybe I've studied in school that okay, through PCA and something, this we can remove this thing. Okay, but that's just knowledge being passed on through generations of practical users. But is it mathematically a mathematically solid way of doing thing or not? So that's what they're trying to show here. And now through this paper, they've shown that yes, irrespective of the data set, as long as yes, that's what they said. If they're highly correlated, you can exclude the other one of the columns probably. So essentially, that's what they're trying to say. So that's what they have mathematically proven here. So that's the idea behind it.
Okay.
Okay, so yes, I think in section 5 they have also given some example. They have not only given this mathematical proof, and also in section 5.3 they have also done experiments with different data sets, and they have shown that okay, it actually works. And in section 6, I haven't studied this, but what they have done is that they have also described the data preprocessing algorithm so that this entanglement is low, or how to come up with. I think so, or it already exists as PCA and all those things. But I don't know what they have. They probably have come up with something more efficient. But I haven't looked at it. And so I'll just talk a little bit about the conclusion and limitation in future work as well. What they have said is that they have only analyzed it for LCNNs with polynomial nonlinearity. I think so. They talk about activation functions here. I'm not sure, but they haven't. Yes, they have said it. Okay, this is what they do. Accounting for neural networks with connectives beyond those considered. Example, connectives that are non-local or ones involving skip connections. This is an interesting topic for future work. That means that although they approved it for LCNNs, whether this works for non-LCNNs or not, that is unknown. That's what they're trying to. That said, that is a topic for future work. That's what they're trying to say. And another thing that I found is that they haven't done it. They haven't trained it on textual data. They have used audio. Yes, they have used audio and image datasets for their examples, but they haven't used text data because I think so. They have mentioned here that they are yes. In contrast, the performance architecture for textual data are typically non-local. So that's why. But the thing is that RNNs use textual data, and RNNs are good for textual data. So why haven't they used it? Okay, that's something that needs to be looked into. That's the okay. That's for future scope. So yes, overall that was the context of this paper. Yeah.